Okay, so in this video I'll be explaining how I did my pathfinding, behavior tree, and finite state machines for my project. So I'll start by explaining how I did my pathfinding for my NPC. So the grid that the NPC will be moving on is this. The pathfinding will be, all the calculations will take place in this grid. And you can see this 4 black cube is the closest path that the NPC can take to the player. And you can see the player is a target, and I can set a speed. So if I turn on move to target, the NPC will follow this path until he reaches the target. And if I move and then I turn it on, the path will update as I move. So the NPC will chase the player. When he reaches the player, he will kill the player. So for the pathfinding to happen, we need the grid map script, which is used over here to create the grid. So how the grid is created is that it creates a vector 2 of the grid world size x and y axis. In the x and y axis, but the y axis is actually the z axis of the plane, because we don't want the NPC to move up, and we can set the node radius. Okay, so this takes in the unwalkable mass, which is this. So it will check if the node will check if it is unwalkable, the position is unwalkable or not. Okay, so the grid size x and grid size y over here is the number of nodes that can fit in the x and y axis of the grid. So to get this, we use this function math f.round2in to get the grid world size that we see on top, and x and the node diameter, which is the node radius times 2. So for example, our grid world size x is 10 and our grid world size y is 10, and our node diameter is 1. So the grid size x will be 10 and the grid size y will be 10. So there can only be 10 nodes in the x-axis and 10 nodes in the y-axis. And after getting these values, we create the grid. So we'll create a new two-dimensional array of nodes, and we will pass in the values of our grid size x and grid size y, which we assumed is 10 just now. So if that is 10, and we'll loop through the grid size x. So loop 10 times, so you'll loop 100 times total, and we'll check if the position the node is in is walkable or not. So if it's not walkable, it will return false, and if it's walkable, it will return true. And then we'll create a new node in the x and y axis that we are currently in the loop. So and then we'll pass in the walkable or not value at the bool, and we'll pass in the world point that the current node is in the world point, in the world position, and then the node position in the grid x and y axis. And then the next is the get neighbors function. So you are passing the node that we want to get the neighbors of, and so you'll loop through the neighboring blocks in a 3x3 block. -1 is the left node and 1 is the right node. So for example, this is the node that we want to check the neighbor of. So, and it has a position of 0. And then this will be the -1, this will be 1. So we'll get the neighbors of the 3x3 blocks over here, and then here. So we'll get all these 8 nodes, and then we'll add it to the list, and then we'll return the list to get the neighbor of the node. Then this is to get the node from the node position from the world point. So it makes sure that the node is not outside the grid, so there won't be any errors. And then we'll get the x and y indices of the two-dimensional grid array, and then we'll return the position of the grid. Okay, so the next script I'll be explaining is the node class script. So this this script implements the iHeap item interface, and then we put in the node, and then it has the public bool walkable, whether if the node is walkable or not, and the node world position, the node position in the grid X and Y axis, the the G cost of this node and the H cost of this node, and the F cost of this node, which is the G cost plus H cost. The G cost is the distance from the starting node, and the H cost is the distance from the end node. Yeah, we will also have a parent, which is later used in the pathfinding script. I'll explain the heap later. So you have this compare to function. So you put in another node for this node to compare with, and we'll compare the F cost. So we want to find the node with the lower F cost. So if the node is the same, if the F cost is the same, we'll just compare the H cost. We compare the distance to the end node instead. And then we'll return minus compare. So why we want to return minus compare? Because if the F cost is higher, it will return 1, which means it has a higher priority. But instead we want the lower F cost to return 1 because the lower F cost have the higher priority. So we reverse it instead. So how does the walkable work? So you can see in this grid map, we use physics.checkSphere on the node to check whether if the node is walkable or not, and then it will be, if it's walkable, it will return true, and if it's not walkable, it will return false. So see here, so this is we don't want the NPC to walk through here, so this range have the layer mask of unwalkable, and there's a collider here that is around here. So this will return unwalkable and return false to the walkable bool. So if you just turn on the script gizmos, you can see that this is the entire thing is straight, and when the NPC does its navigation, it will just ignore this area and bypass it instead. So now I'll be explaining the heap class and the heap script, and why did I use a heap sort instead of just using an open and closed list. So the reason why I didn't use an open and closed list to keep track of all the nodes is because it will get very slow once the open list gets bigger. So because in order to find the node with the lowest F cost, we have to loop through the entire list to find every single time we want to find the node with the lowest F cost. So if our grid expanded, or we will have more and more NPCs in the game, it will take very long for the pathfinding in order to find the path, and then it will slow down the game. It will slow down the game in general. So we use heap sort to speed up the pathfinding process. So how the heap sort work is we can add a node to the heap. So the first heap we add will be 0. So each item in the heap sort can only have a maximum of 2 child. So for example, like this is the parent of these two, and this is the parent of these two, and this is the parent of these two. So they have a heap index of 0, 1, 2, 3, 4, 5, and 6. So this is their heap index. So we set a heap index over here, and when we add a new item to the end of the array, which is this, the last item we add, we'll sort up the item. So what does the sort up function do? So sort up. So for example, this has the lowest F cost. So this has the F cost of, okay, so let me change it to F cost instead of the heap index. So for example, these have a 2 F cost of 2, the F cost of 3 and 5, this F cost of 10, 11, and F 7 and 9. Okay, so the parent will always have a lower f cost than its child. So you can see, and the sort out function is we'll find the parent index using this formula, and we'll compare the new node that is added, which is here. We add the new node that is added. We'll compare this with the parent. So for example, if the new node added has a f cost of 1, we'll compare with the parent. We'll compare to a parent here. If the node has a lesser f cost, we'll swap this 1 with the parent. So this will become 1 and this will become 5. So we'll swap both of their position, and then you'll check again because it's in the while loop. So you'll check again. So this 1 has a lower f cost than the very first one. So you'll swap again. So you'll swap position. So this is much faster than than looping through the entire list, because we don't loop through the nodes on the right side. We only loop through one node, and we only loop through twice instead of looping through the entire list. So it's much better performance wise. And then if we want to remove an item, so we want to remove the very first item, so which is the item with the heap index of 0 on the very top. And then we will minus the current item count because we are going to remove it, and we'll set the last item. So for example, we want to remove this, we'll set the very last item, which it is, to be here, and we'll remove this. We'll set the last item to be a first item of the heap, and then its heap index will be 0 because it's at the very top. This has the heap index 0, 1, 2, 3, 4, 5. So it has a heap index of 0. And then we'll sort down. So what the sort down function does is this is the formula to get the left child, and then this is the formula to get the right child. So this is a heap index of 0. So if you times 2, it's still 0. So and then you plus 1. So this heap index of 1. So this is how we get the left child, heap index of 1. And then this has a heap index of 2. So 0 times 2 is 0, and then plus 2, heap index of 2. So this gets the right child. And then we check if this heap has a left child. If it has, we will check if the left child have a lower priority than the right. And then it does. So we swap this 5 with the 3. And then because it's in a while loop, so it will do the same thing. So you'll check again. You'll check the right. And then this has a lower f cost than this 2 has a lower f cost than the 3, so they'll swap again. And then this will be the top of the heap with the lowest f cost. So by using the heap sort is much faster than performance wise than using an open list, because we don't have to loop through every single item in the open list. So as you can see, we did not need to loop through these three items at all. And then it gets better if the heap gets very, very big. So it's better performance wise, and then exits the loop. So the next script I'll be explaining is the pathfinding script. So what this script does is it does all the calculations that will find the shortest path from the start position to the target position with the start and end node. So first we create an array of waypoints, and we should store the waypoints for the shortest path from the start to end, and then we'll get the position of the starting node and the target node, or the position of the node it is on, that they are on. Okay, so if the start node is walkable and target node is walkable, we will proceed with all this. Otherwise we don't, because Otherwise we do nothing, because if they are not walkable, it means they are out of the map or cannot be reached, unreachable. Okay, so first we create a open set, which will have a new heap of nodes, which will have the size of the grid max size, which is the size of the entire grid, the number of nodes in the entire grid. And then we have a closed set of nodes. So the open set is the nodes that have not been evaluated yet, and then the closed set contains the nodes that have already been evaluated. And so we start off by adding the starting node to the open set, and then we'll evaluate the node. So we'll start by removing the first item of the heap, which is always the one with the lowest F cost, like I explained just now, and we'll add that node to the closed set because it has already been evaluated. And then if it is the target node, then we will return path success true. If not, we will continue with this loop. So we'll get the neighbor of the current loop, so of the current node. So for example, we just passed in the starting node, so this is the starting node, and then we'll get the neighbor, so we'll get the 8 neighbors. So this is the 8 neighbors, and then we'll check if the neighbor is walkable or not. So if it's unwalkable, or if it's already in the closed set, we'll ignore that node. So, and then we will continue evaluating the rest. We'll just continue the loop, and then we'll check the cost to move from the current node to the neighbor node, and then which is the g cost plus the get distance from current node to neighbor, which is the get distance function is so one move in the x-axis is it costs 10, and then one move in the y-axis also costs 10, and then one move diagonally has a cost of 14. So we'll find the cost to move to the neighbor, and then if the new movement cost to the neighbor is lesser, or the neighbor is not in the open set, we'll calculate the g cost of the neighbor, and then we'll give the new g cost to the neighbor and calculate the h cost of the neighbor, and then we'll set the neighbor, the parent of the neighbor, to be the current node. So for example, this is the node that we'll be moving to, so we'll move to this node. This is the second node we'll move to, and then we'll set the parent of it to the starting node. So the parent of this node is the starting node, and then if this node is not yet in the open set, we will add it to a neighbor. We'll add it to an open set. If it is, we'll just update a neighbor. So if it returns path success, which means we found a path already, we'll retrace the path. So for example, this is the end target, and then this is the shortest path. So the parent of this is this, the parent of this is this, and then this is the path, but the path is from the end node to the start node. So we have to reverse this path to get the path from the start node to end node. So what we use this function, so we'll create a new list of paths, which contains a list of nodes, and then we'll trace the path backwards. So the current node will be the end node, and then we will, while the current node is not the starting node, we'll add the current node to the list of nodes, and then we'll set the current node to be a parent. So this is the first in the list, and then we'll set it to here. The second node in the list is the parent of the end node, which is this, and then we'll keep looping through until the current node is the start node, and then we'll reverse the the list of nodes, the path, and then we'll get the path from the start node to the end node. And then the simplify path, so we don't want the NPC to move to every single waypoint in the node, which is, as you can see, is each of the nodes is very tiny, so we don't want the NPC to move to every node and check. We don't want that, so we simplify the path by only adding the waypoints, which is where is it, here. So waypoints, we simplify the path, so we only add the nodes that the NPC had to turn to the NPC will turn into the waypoint. So the NPC will turn here, will make a turn. So if it's a straight path, for example like this, the waypoint will just be from here to here. So there is no need for so many checks of the waypoints. So we simplify the path we'll check if the direction is different. If the direction is different, we'll add to the waypoints array. Okay, so we get so this function gets the distance between both nodes, and we'll check if so we are passing two nodes into this get distance function, so node A and node B, and then we'll check the distance of the node A and node B in the x and y axis, the difference, and then we'll calculate the number of diagonal movements and vertical or horizontal movements needed to move from node A to node B. So each for example, this node A, this is node B, and then these are all the nodes. So calculate, it takes one diagonal move and one horizontal move to reach from A to B, and then calculate the cost of it. So one diagonal movement will cost 14, and then one horizontal or vertical movement costs 10. So from A to B, it costs 14 plus 10, which is at a cost of 24. So that's what this does. So you return the in of the cost need to move from the node A to node B. Okay, so for the last pathfinding script I'll be explaining is the unit script. So this is the script that is directly attached to the NPC, and it's the script that will make the NPC move to the waypoints and to a player. So what this script does is if the path is found, is successful, it will set the waypoints that is passed through here will be set to the path of vector 3 array that I created on top. So these waypoints will be the path, and then we reset the target index, and we'll start this coroutine. We'll stop the coroutine first, and then we'll start the coroutine. So this is the follow path. So this method will allow the NPC to move to a player. So the current waypoint is the first vector tree of the path array, and then we'll have the NPC look at the waypoint in this, and then if the position is at the current waypoint, we'll increase the target index, and we will change the current waypoint to the next waypoint in the array, and then we'll move to the target, and if move to target is true, the bool over here, and we will move the NPC to the next waypoint using this speed, and then once the NPC is at a player, which is here, and if the NPC is near the player, we'll set the target to be the player, and if the player is in the attack range, if the player is in the attack range, the NPC will the player is in attack range, the unit dot move to target will set to false. So the NPC will stop moving towards the target, and then the NPC will attack the player. And then the NPC will attack the player, and if the player is still in the attack range, or the NPC has not attack finished, then the NPC will wait 3 seconds before he can attack again, which is the cooldown timer counter that is in the that's here. So that's the cooldown timer. So if it's greater than 3, the NPC will attack the player and reset the counter. Or if the player is so after the attack has finished, this bool will be set to true. Attack finish will be set to true using this animation event. So attack finish true, and then if once attack finish is true and the player is in chase range, then the NPC will chase the player over here. The move to target will be set to true again, so the NPC will start moving to the current waypoint and chase the player, and then the walking animation will be set to true. And if the player is outside of the chase range, the NPC will just change to idle state, and if it's in attack range, the NPC will attack. And for the idle state, the walk animation set to false, so it's in the idle animation, and move to target set to false, so the NPC will not chase the player. And then if the player is in attack range, he will attack, and if the player is in chase range, NPC will chase the player. Okay, so the take damage state is any state transition. So whenever this method is called, take damage method is called, the NPC will transition to a take damage state, and then the enemy can only stagger once every 3 seconds. So you can see the counter here increasing it by time.delta time. So you can only trigger this take damage animation once every 3 seconds, and then it will reset the stagger counter. And then the reason I want it to only stagger every 3 seconds is because I don't want the NPC to be stuck in this as you can see just now, in that stagger animation like this. So if he keeps getting stuck in that animation, he won't be able to do any other attacks or whatever, any other animation. So if he has no health, he transitions to the die state and then die. Yeah, if he has 0 health, he'll transition to this die state, and then the die animation will play. So if you have noticed just now, the NPC also has health, and then this function updates the health. Yeah, and all these to check for a player, and the animation events. When the attack animation finish, this bool will be set to true, and when on the attack hit, then the target dot take damage, which is the player, so the player will run this take damage method in the player. So I think that's it for my NPC explanation. So I'll move ahead to explaining my behavior tree now. Okay, so now I'll be explaining my dragon and how it works. So how my dragon works. So he starts out in the sleep animation over here, and then you can see he's asleep, so nothing's happening. So if you walk close to the dragon, this awake tree will play, and then her work is forced, and then everything else will play. So if he's in the attack range, the dragon can attack the player like this. Then if I walk further, and then he will go idle into his idle states. And then if I go closer, he'll start chasing me. Okay, so if I hit the dragon also has a stagger counter, so he don't get stuck in the in the take damage animation always. Okay, so if I hit the dragon to 100 health, he'll go into his fly animation tree. So he'll go into fly mode and then he'll blow flame attack, and then he will land. Then he'll continue attacking me. Then if I kill him, he dies. And then he will play his die animation. Yeah. And then if so I make him chase me all the way. I have him chase me all the way here, and then I set my health to 50. Okay, so you can see he's currently in the chase state. If he kills me, he will go into his sleep state, and then he will walk back to his sleeping spot, and then he'll go into his sleep animation again. And then when he dies, this is the tree that will play. So this is the tree that will happen. So if he dies, nothing else will happen, and if he's sleeping, nothing else should happen. And if he's flying, nothing else should happen. So that's my dragon behavior tree. And then so for the animation event, so this is the on bite player event. So if he bites the player will take damage, and he blows fire, the flamethrower will be set to true, and on fire when he blow fire finish, and he will land. Flamethrower set to false, and he will land. So these are the tasks that the dragon will use. So this checks if the player is within the certain distance from the dragon. This is the scream. They will trigger the scream animation and set the dragon to awake. This has awoke, you will return whether the dragon is awake or not. And this is the chase player. You will look at a player, you will transform.look at function, and then you will return true and chase the player. It's idle. So the dragon will stop the Nefmesh agent, and then the dragon will go into idle. And this returns if the player is in attack range, which is using this. If the player is in the on trigger enter in the boss collider range, then this will be set to true, and this will return. And then he will attack the player. First he look at the player, and then he will play the bite attack. And then this checks if the player is dead. If the player is dead, he will move back to sleeping, which is this task right here. So he will set the destination to his sleeping spot, and then you will enable the Nefmesh and enable the walk animation. And then once the dragon is at the sleeping spot, then you will stop the walking and trigger the sleeping animation, and the dragon cannot be hit. And then this task returns success. And this checks if the dragon is dead. If it's dead, then this tree will play, and then the die will play. The animation will play, and then the dragon dies. This is fly mode, return if the dragon is flying or not. And this, if the dragon is flying, then if this is true, then enable the animation and disable the idle and walking animation, then return the task is succeed. This method gets the distance between the dragon and the player, and these methods look at have the dragon look at the player. Okay, so and then this is the script for flamethrower. So for every 0.5 second the player is in the fire, the player will take 50 damage. So whether he enters and when he stays, so he'll take damage as every 0.5 seconds if he stays in the fire. So it's not one shot he die, he will just take damage every 0.5 seconds. I think that's it for my dragon explanation. So this is the die method. So if the health is 0, then dragon dead is set to true, and then this is dragon dead will return with this whether will return this dragon dead. And this checks at every update whether the dragon is dead or not. I think that's it for my behavior tree explanation. So the next, I'll explain my player next. My player finite state machine next. Okay, so now I'll be explaining my character finite state machine. So I'll start the character off with 20 HP. So this is the player HP. So the character starts out in the standing state, and he can draw, shift, punch, draw. So the added animations is punch, take damage, and die. So if the character is 0 HP, he will die, and the NPC will scream. And if he doesn't draw his sword and then he press the attack button, which is J is the attack button, he will punch. And if he draws his weapon and press the attack button, he will swing. And the button to shift and draw is Q, so they are the same button. Okay, so so all the states over here is the draw state, the shift state, the swing state is all inherited from the standing state. So the only thing that each of these state does is to trigger the animation, and all the logic is done in the standing state. So there's this there's 5 bull, jump, crouch, draw, punch, and swing. And if the character crouch, if the crouch button is pressed, then you'll change to a ducking state. And if the jump button is pressed, you'll change to a jump state. And if the draw button is pressed, which is Q, and the weapon is the weapon is not in hand, which is I created this bull here, which is there's 2 new bull. One is weapon in hand and one is dead. So his weapon in hand will be set to true when the player draws his weapon. So I find the draw weapon. So his weapon in hand is true. Then if he shifts the weapon, his weapon in hand is false. So this checks whether the character is currently holding a weapon or not. So if you press the draw button and the character is not holding a weapon, then he will draw his weapon. It will transition to the draw state. And if you draw and the character is holding a weapon, you will change to a shift state. So he will shift the weapon. And then if he swing and he's holding a weapon, then it will change to the swing state. So if he's holding a weapon and he attack, he will change to a swing state. Else if he punch, which is also the same control as swing, which is J, and he's not holding a weapon, so I shift and I press J, he'll punch. And if the character health is 0, he'll change to the die state. So all of these functions, all of these states all inherit from the standing state. Cause I think that makes sense for me. So even take damage state. So take damage state, when you enter this state, you update the player health. The player health text over here, and you only trigger the take damage animation if the player health is greater than 0. And after doing all this, you will change back to the standing state. And there's the die state, which also inherits from the standing state. So if the player health is 0, the player health is 0, then your the the character dot date over here is set to true, and then you will just trigger the die animation, and we change the collider height so that the player will lie on the ground. If not, the player will just be floating. So these are all the states for my player. So, and then the other states are the take damage state, the punch state, and the die state. I don't think I have added anymore. Oh, and the player will have a hit enemy function. So there's a target. Where is it? Target. Yeah, current enemy. I mean, current enemy. So this is the current enemy. So if on trigger enter over here in this boss collider. So if the enemy enters this boss collider, the current enemy will be set to the enemy game object. And if it exits, then you are set to now. So the tag enemy is actually the dragon, and the NPC tag is actually the NPC. So when the player swings his sword, we go to this character animation event. So we get the character script, and then over here, because we want to use an animation event, so and then the animator is on this chibi human instead of the character. So we have to use another script to do the animation event. So when on swing hit, which is over here, where's the swing sword? So over here, on swing hit, when he swings the sword and he hits the enemy, you will run the hit enemy function. Where is it? Close the rest. So run the hit enemy function, and then we check the tag of the current enemy. So if it's the dragon, we'll run all these, and we'll disable the NPC UI, and we'll enable the dragon UI, the text. We'll get the dragon controller, and if the enemy is null, or enemy health is less than 0, or if enemy cannot be hit, then we stop the function here. We don't execute any of these, and then we will minus the dragon health according to the damage passed in, which is the damage of the player. Player dot damage here. I think it's above damage. Over here, so we can set the damage in the inspector, and we'll minus the health according to the damage, and then we'll update the dragon HP UI, the text to reflect the new health after it's deducted. And then if the enemy stagger counter is more than 2, not more than 2, then we don't execute the rest. If not, if it's more than 2, then we can trigger the animation and reset the stagger counter. So the reason why I want it to be more than 2, and then we can play the animation, is because the take damage animation is because I don't want the dragon to have this, to run the take damage animation every time he gets hit. That means if he does that, he will be stuck in the animation and he will not be able to attack or do anything else. And if the player is NPC, then we get the NPC controller, and we'll disable the dragon text and enable the HP text. So, and then if the enemy health is more than 0, then we'll run the enemy.take damage function, which is over here, and then which is over here, take damage, and then the NPC will transition to its take damage state. I think that's all for my for my explanation of my project. Thank you.